Trigonometric equations, these ones will use double angle formula and addition formula to solve them. Example 1. Solve sine 2x plus cos 2x is equal to sine squared x plus 1. The first thing we want to look at here is substituting in for our sine 2x identity, where sine 2x is 2 sine x cos x, for our cos 2x identity, where cos 2x is cos squared x minus sine squared x, and also for the 1 on the other side, just so that we can eliminate a cos squared term in between here. When we do this and collect all our like terms, we can see we get the equation 3 sine squared x minus 2 sine x cos x is equal to 0. Now this is a little bit of a problem for us because we don't like to have equations that have sines and cosines in them. So if we divide both sides by cos squared, remembering that sine squared on cos squared would be tan squared, we get a nice equation that only involves tan. 3 tan squared x minus 2 tan x is equal to 0. We can then factorise that by pulling out a tan x and find our solution. So that gives us tan x is equal to 0, or tan x is equal to 2 on 3. Working through and knowing what values of tan give us 0, we know that x will be 0, pi and 2 pi, given we have the bounds 0 is less than or equal to x is less than or equal to 2 pi. And using our calculator for the other one and remembering that tan is positive in the first and the third quadrants, we get 0.588c, or pi plus 0.588, which is 3.730. Remembering the c just tells us that it's a radian measure. Okay, in example 2, we are given the equation that 2 cos x minus 1 is equal to 2 cos 2x. And we're told to show that cos x is equal to a quarter outside of 1 plus root 5, or a quarter outside of 1 minus root 5. Now notice we haven't actually got any bounds here because we'll get cyclical answers anyway. So let's just start off. Our first step will be to substitute in for our cos 2x. Now remembering that cos 2x is cos squared x minus sine squared x, but once again we only want to have this in terms of cosine. So we'll replace the sine squared with a 1 minus cos squared to get 2 cos x minus 1 is equal to 2 outside of 2 cos x squared minus 1. Collecting all the like terms and simplifying it, we'll get a nice quadratic equation of 4 cos x squared minus 2 cos x minus 1. Now, there's a bit of a hint in the question here that we've got cos x is equal to 1 quarter outside of 1 plus root 5, or 1 quarter outside of 1 minus root 5. That tells us that it's obviously not going to factorise easily because this is the quadratic equation in cosine. So we'll use the quadratic formula straight away. Plugging it straight in, we get 2 plus or minus 4 plus 16 on 8. We already know what the answer should be, of course, which if we simplify the third and divide by 2, we get what we were required. Our final example is going to be from the 2008 HSC question 6. It can be shown that sine 3 theta is equal to 3 sine theta minus 4 sine cubed theta for all values of theta. And you could do that by using the addition formulae. But it specifically says don't prove that, so don't do it. But obviously we're going to have to use that somewhere. Use this result to show that sine 3 theta plus sine 2 theta is equal to sine theta for those bounds. Okay, so our first response here is going to be, well, obviously we need to substitute in for our sine 3 theta with our 3 sine theta minus 4 sine cubed theta plus sine 2 theta. Our next step will be to use the sine 2 theta identity, where sine 2 theta is 2 sine theta cos theta, and substitute in for that. Our next step will be to get rid of the 2 that's a leading coefficient, so dividing everything by 2. Our next step will be to factorise. Now, if you look at that, you'll notice that we have sine theta as a common factor for each of those terms. So if we pull that out the front, we've got 1 minus 2 sine squared theta cos theta. Now, from this point on, once again, we want to factorise the inside bit, so we've got a bunch of different factors is equal to 0. To do that, we'll need to substitute in for sine squared theta, remembering that 1 minus cos squared theta is sine squared theta. I would suggest taking your time and writing this out very slowly and not trying to skip steps here because you'll lose signs and just make silly errors. If we substitute that in and then simplify, and factorise that quadratic expression. Now we've got a nice easy quadratic to factorise in the middle there, and we have 3 different roots or 3 solutions to that. So we should write out all those solutions. So obviously for 3 things to multiply to give us 0, either the first one's 0, so sine theta is 0, or the second one's 0, so cos theta is a half, or the final one, which is that cos theta would be -1. And looking once again at our bounds, 0 to 2 pi, we can find some solutions. The first one will be 0 for the sine theta equal to 0. Pi on 3 and 5 pi on 3 satisfy the cos theta equal to a half. Oh, pi also satisfies sine theta equal to 0. No, that's wrong. Yes, no, that's right. And 2 pi satisfies both sine theta equal to 0 and cos theta equal to -1. Like with all these questions, make sure that all your solutions are within the bounds of the original question.